Okay, so we already talked about how to integrate odd powers of cosine and also even powers of cosine and sine. But now what I want to do, even though it should be a little bit more straightforward now that you know how to do it for cosine, I'm just going to show you a few examples that involve odd powers of sine just so that you get a better idea of what the method involves. So in essence, when we have an odd power of sine of cosine, what we do is we break it down into sine x, in this case, times sine squared x. So the idea behind that is that you can replace this by using the trigonometric identity plus cosine squared x equals to 1. So now you rearrange this, so you solve for sine, so this gives you 1 minus cosine squared x. So you substitute that in here, and you're going to have 1 minus cosine squared x dx. And now what you can do is you can make a substitution. So in this case, what you could say is, let's have u equals to cosine of x, such that du equals to minus sine of x dx. And then what you do is, you, in order to transform this integral, you multiply the outside by minus, and then make the substitution. So you're going to get 1 minus u squared times du. And now you just integrate this as you normally would. So this is going to be minus u plus u cubed over 3 plus some constant c. And now you just substitute back in here. So you're going to get minus cosine of x plus cosine cubed x over 3. Alright, so this is essentially how you get that. And if you wanted to do it for higher powers of sine, so let's generalize this. If you have sine to some odd power m, and we take the integral of that, then what you want to do is you want to break this down. So you're going to have sine x times sine of m minus 1 x dx. And now you know that this quantity here, because you have an m is an odd number, so if you subtract 1 from an odd number, it becomes an even number. So let's turn it into something like 2n, where n is just any integer. And the reason for that is that we know that 2 times n is always going to be an even number, and same goes for m minus 1. So we have this here. And now what we do is we just replace that here. So we're going to get sine of x sine 2x. Actually, it should be 2n x dx. And now from here, what we can do is we can take out that n as a power. So this is going to become sine x times sine squared x to the power of n. And now we make the substitution in here, which is going to be sine of x, then 1 minus cosine squared x to the power of n. And then keeping that in mind, what we can do is we can just make a substitution here. So we can say u equals to cosine of x, and then du is going to be equal to minus sine of x dx. So now this integral is going to become minus u minus u squared to the power of n du. So now it all becomes a problem of just expanding this out in terms of n, and then substituting back for cosine of x to get the final answer. So this is extremely similar to what you would do with cosine of x, but essentially you just need to know that this is the kind of substitution you make. So that is the general idea behind integrating odd powers of sine and cosine. And obviously it gets a lot more tedious when you increase the power here, but obviously you wouldn't really take into account those kind of cases in which you have really high powers, because those don't happen in application as often as you would think. So as long as you know how to handle these ones, I think it should be alright. These techniques are quite useful, so sometimes you can make simplifications like this just to simplify the problem, bring it down to something that you can actually solve using your regular methods of integration.